With cardiac dynamics, cardiac output uh, equals heart rate multiplied by stroke volume. Now, cardiac output is measured in litres per minute, heart rate is measured in beats per minute, and stroke volume is measured in millilitres. Typical values for each of these. So in resting, a typical value of heart rate would be 70 to 72 beats per minute. Stroke volume would be 60 to 80 millilitres, and multiplying them together would give you a cardiac output of approximately 5 litres per minute. During submaximal exercise, heart rate on average is 100 to 130 beats per minute. Stroke volume would be 80 to 100 millilitres, and multiplying heart rate by stroke volume would give you an approximate cardiac output of about 10 litres per minute. Now in maximal exercise, heart rate, your approximate maximum heart rate is 220 minus your age. So for a 20-year-old, that would be 220 minus 20, meaning that their maximum heart rate would be 200 beats per minute. Stroke volume is approximately 100 to 120 millilitres, and that then gives a cardiac output of approximately 20 to 30 litres per minute. As you can see on the diagram to the left, as intensity increases, so does stroke volume, until the intensity is approximately 40 to 60% of their VO2 max, and that's when stroke volume then begins to plateau. This is because stroke volume is the volume of blood that's injected out of the left ventricle per contraction. And heart rate is the number of times the heart goes through the cardiac cycle per minute. So as intensity increases, that means both heart rate and stroke volume are trying to increase as well. And because heart rate is increasing, that means there's less time for the cardiac cycle to occur, and that means then there's less time for specifically diastole to take place, so for blood to flow into the atrium or the atria, and then systole, atrial systole, forcing the blood into the ventricles, and the ventricular systole forcing the blood out. But then if there's not a maximum amount of blood in the atria, then stroke volume would then plateau, as there's not enough time for the atria to fully fill with blood. The graph on the right shows heart rate, the heart rate's response to varying workloads. So the black line shows a lower intensity, so submaximal intensity of exercise, and you can see there's a slight increase before exercise begins, and that also is anticipatory rise. So heart rate also increases due to anticipatory rise before the beginning of exercise, and then as you can see there's then a steep gradient, so a steep increase or a rapid increase of heart rate as just as exercise begins, and then that levels out a bit into a shallow increase, and during submaximal exercise there would then be a plateau of heart rate as they've reached their constant effectively threshold, and then when exercise stops and the recovery period begins, there's then a rapid decrease of heart rate, and then followed by a shallow decrease before heart rate then returns back into the resting of 70 to 72 beats per minute. This is similar to maximal exercise, where there's anticipatory rise, and then exercise begins, causing a steep increase or a rapid increase, followed by a shallow increase. But there isn't usually a plateau, just a continuous shallow increase. And then once exercise stops, there then once again is a rapid decrease, followed by a shallow decrease, but obviously would take more time to get back down to the resting heart rate compared to the submaximal exercise. Now, controlling of the cardiac dynamics, the feedback section of this would be from the baroreceptors, and these baroreceptors are located in the carotid sinus and the aortic arch, and these send impulses or feedback due to the stretch, and this stretch is caused by the blood pressure. So this feedback would be sent to the ANS, specifically the medulla oblongata, and specifically the cardiac control center within that, also known as the CCC. And when there's a high blood pressure, there's a high stretch. So if there was high blood pressure, the CCC would then try to lower that blood pressure. So it would send an impulse down the parasympathetic nerves, which would go to the SAN and inhibit the rate at which it's sending impulses to cause the heart to beat. So the parasympathetic nerves would therefore decrease heart rate, or try to decrease heart rate, to then lower blood pressure. And this and while this happens, vasodilation happens in the blood vessels to also decrease blood pressure, as there is less volume of blood pushing against those blood vessel walls. Oppositely, if there's a low blood pressure, the CCC would send impulses down the sympathetic nerves, which also travels to the SAN, but this time causes the SAN to respond quicker, so causes the heart rate to increase, and also the stroke volume to increase, and also they would cause vasoconstriction in the blood vessels to try increase blood pressure. And then obviously if there was a normal blood pressure, there would be no response, as that is the blood pressure the body wants. Going to blood pressure. Blood pressure can be measured by using cardiac output multiplied by the resistance, with blood pressure being measured in millimeters of mercury per litre. Cardiac output, we know, is measured in litres per minute, and resistance is measured in millimeters of mercury. A healthy blood pressure would be 120 over 80, which is the usual values for it, with the 120 being the systolic blood pressure and the 80 being the diastolic blood pressure. So systolic is when the heart is contracting, and the diastolic is when the heart is relaxing. Resistance can also be known as peripheral resistance. So that's how difficult it is to pump blood through these blood vessels. And this can be affected in different ways, one of which is blood viscosity. So that's how thick the blood is. So if the blood is thicker, then it will flow. It'll be harder to flow and flow slower. Therefore, it's more likely that more blood will build up causing the blood pressure to increase as it can't flow as quickly as normal. Vessel length also affects it, as well as vessel diameter. So if the vessel is quite small, then obviously there's a lot of blood trying to get through at once. So with a small diameter, there's more blood pushing against the walls of that blood vessel, causing a high blood pressure. And during exercise, vasodilation can take place. It does take place. So looking at the graph on the far left, peripheral resistance decreases as the performer gets closer and closer to their VO2 max percentage. And this is because the body requires more oxygen as a greater oxygen debt. So wants the blood pressure to be as low as possible, so that blood, not low as possible, but a healthy amount, so that blood can flow as easily as possible through to the working muscles, as this blood, as the red blood cells containing the hemoglobin is carrying the oxygen. So the oxygen needs to travel through the blood to get to the working muscles, so it can diffuse into the working muscles. The diagram in the middle, now this shows the change in blood pressure during exercise. So during dynamic exercise, you can see that as the intensity increases towards their VO2 max, the systolic blood pressure increases, as this is the pressure of the heart contracting. So as the stroke volume increases, that means it's pumping blood at a greater force, causing the blood pressure on the blood vessel walls to be higher. So that's why the systolic blood pressure is increasing. The diastolic blood pressure doesn't increase that much, though, as during diastole, the heart is relaxing, so there's not any extra blood being forced into the heart, so the diastolic blood pressure would be quite constant. And the diagram on the far right, now this shows the pressure of the blood pressure as it travels through the body. So as it just exits the heart, with the aorta and the arteries, the blood pressure is very high, but as it travels through the arterioles, capillaries, venules, the blood pressure then becomes quite low until it returns back to the heart through the vena cava. During isometric exercise, however, systolic blood pressure increases, but diastolic blood pressure also increases, differently to dynamic exercise, where diastolic blood pressure was constant.